Hey guys, in this video we'll be talking about projectile motion and introducing some of the ideas that I think are really important to understanding the overall topic. We're not going to perform any calculations just yet, but a lot of the things that we discuss in this video will definitely help prepare you for those calculations down the line. Now, if you haven't worked with a projectile before, this is perfect, okay? If you've already learnt it, I still think it's just as important to revise on these simple yet generally overlooked ideas. Exam questions tend to bank on the fact that students forget these tiny details, and so in that regard, I think this is quite helpful. Before we jump into the topic itself though, let's make sure we're all on the same page. For projectile motion, you will need a decent grasp on things like displacement, velocity, and most importantly, acceleration. Okay, acceleration is super important. Those things will be assumed knowledge, so make sure you guys brush up on those ideas. But with that being said, let's get started. Projectile motion. We'll start with the definition. If you've had a chance to read through any definitions, they tend to revolve around just one idea, and that is free-falling objects, right? Projectile motion refers to objects undergoing some kind of free-falling motion. And what they mean by saying that is just basically an object that's traveling under the influence of one thing only, okay? That one thing is gravity, yeah? So I have a couple of pictures on the screen here just to contrast that idea, what makes a projectile basically, and our two examples down at the bottom, they are examples of projectiles, right? Now, just to quickly digress, generally speaking in projectile motion, you'll see that there is some kind of initial launch velocity. That's definitely a hallmark of projectile motion. So you can see, you know, the soccer ball being launched or being kicked by the soccer player. Similarly to the cannonball, that's, you know, the gunpowder explodes, it propels the cannonball away. So in both cases, there's some kind of initial launch. But if we follow along with the trajectory, we notice that as that object is traveling through its path, there is nothing influencing it except for gravity. Now remember, gravity is a downwards influence. It's something that pulls things downwards, yeah? To be more specific, it's a vertical influence, right? So in this case, or actually that's less specific, but in this case, both objects, right, eventually come back down because gravity is pulling on it. And that's the thing with projectile motion. They are objects that only have the influence of gravity as they're traveling through. Kind of contrast that with the two examples up top, left-hand side, missile, right? Yes, it's launched, but if you think about it, there is a propulsion system that continues to dictate its motion after that. There's, you know, gravity is not the only thing controlling its motion throughout its trajectory. Compare that to Michael Jordan, right? Him going for the slam dunk, his right hand literally dictating the motion of the object. Gravity is not really the main player there. I mean, if he was going for a free throw or a three-pointer, you know, perfectly fine. That is projectile motion. You know, as the ball leaves his hand, there is no longer any other input from anyone or anything except for gravity, right? And that's what free falling is. So the thing is, you know, gravity, just to kind of clarify this downwards influence. When we say influence, we really mean acceleration, yeah? So there is a downwards acceleration. Now, in projectile motion, the way that we write it is there is a bit of a funky notation, but we call this y double dot, and you might see this as minus g, and that minus g just represents minus 9.8. Minus 9.8. And I'll put units in as well, meters per second squared. That is going to be the gravitational acceleration that we always assume in this topic. So I guess in this topic, there are two assumptions that we make. And I want to make sure that you guys are really comfortable with this, because no matter how difficult the question is, you should always be able to come back to the ground truths, basically, right? These assumptions, they're like your security, yeah? You can fall back to them and trust them. That is, the vertical acceleration is always minus 9.8, right? So it's a fixed value, it never changes. And then the horizontal acceleration, so the way that we represent horizontal acceleration is we go x double dot, right? This is going to be 0 meters per second squared. So these are our two assumptions that we take into this topic. You might be thinking, wait, what about friction? What about air resistance, right? Wouldn't that slow things down? Wouldn't that cause for an acceleration in the horizontal direction? That is technically true, right? But these are the assumptions that we make in Year 12 Maths 3 unit, right? Extension 1. We consider those effects negligible. So we basically say there's nothing in the horizontal direction. Now remember, I just want to clarify, when I say the vertical acceleration is minus 9.8 meters per second squared, what I really mean is, you know, if an object is falling, If an object is falling, right, that object, as it's falling, for every second it falls, it gains 9.8 meters per second in velocity, right? Or I guess if I throw an object upwards, as it's traveling upwards, for every second it's traveling upwards, it loses 9.8 meters per second in velocity. And that's because gravity is a downwards influence, a downwards acceleration, right? And that's basically it. Now, when I say horizontal acceleration is 0, I mean literally as the object passes by, horizontally speaking, there is no change in its horizontal velocity. Yeah. So you probably noticed that I'm really emphasizing the components of the projectile instead of just looking at the projectile at face value. And that's exactly how we're going to tackle projectile motion, analyzing these guys, right? The analysis starts with the deconstruction of the motion down into their respective components, and then all the insights come from there, okay? So we've already done that with the acceleration. When we haven't looked at the acceleration as a whole, instead we've looked at it as components, right? And this is best obviously visualized with vectors. So you can see here projectile motion, basic projectile motion, but at each phase we've drawn in its acceleration vector. Let me just clarify. This is our acceleration vector. This is important because we're going to look at the velocity vectors, which look completely different in a second. But here you can see you have a downwards vector. They are all fixed size because they never change, right? This is your minus g the whole time. There's no horizontal one because horizontal acceleration is 0, right? There is no magnitude for you to draw anyways. But that's basically it, right? So I think it's really important that you, when looking at projectile motion, you're ready to deconstruct it. You need to think about, when you look at this thing, you need to think about it as a combination of two motions instead of just thinking about it as one motion, right? It's the fact that you combine horizontal and vertical, combining those two arrives at this parabolic trajectory. That's how you arrive at this projectile motion, right? Where, now just to clarify, your horizontal motion is very different to your vertical motion, but because they're different, that's the reason why you get this very unique shape. You get the parabolic trajectory, right? Now, let's have a look at the velocity vectors and how they change over time, I guess, under the influence of the gravity and of the accelerations that we've established so far, right? If we look at the velocity vectors, you can see that, you know, at any given point, the velocity vector is going to be like this tangential vector, and this is your overall velocity. But once again, we don't look at projectile like that, right? We kind of we deconstruct things into their components, and so instead of looking at the overall vector, let's look at the components instead. Let's look at the vertical ones first. So like these guys, which represent the vertical component of the object's velocity. You can see, oh, there's none there, but you can see how it's changing and how this is a direct influence of gravity, right? It starts off with some kind of some vertical velocity because it's traveling upwards, but that vertical velocity decreases until it reaches the max height where vertical velocity is 0, okay? Vertical velocity is 0. There's still a horizontal one, okay? And then obviously after the max height, you can see the vector grow in size, yeah? And that is obviously gravity accelerating it. It's picking up speed like we were talking about before. For every second it falls, it gains that 9.8 meters per second of velocity, right? And that's how it behaves. And obviously a clear correlation between what we're seeing here and what we established earlier with the acceleration, right? Now let's have a look at the horizontal one, right? Horizontal, we said acceleration was 0. So in the horizontal direction, if there's no acceleration, your velocity shouldn't change, right? It's exactly what we see. You can see here, the horizontal component is always the same. If you have a horizontal component of 2 meters per second, it will be 2 meters per second the whole way through. There should not be anything that has changed that one component, right? And remember, I'm speaking very strictly about the horizontal component of the velocity, not just the velocity in general. We speak about the components of things instead of just the overall things, right? But yeah, that's basically, I guess, the gist of how projectile motion is encapsulated through that. In the next lesson or in the next video, we'll touch on to the calculations, but I just want to wrap up by reminding you guys, right? Our ground truths here is that in your horizontal direction, there is no acceleration, 0 meters per second squared. And in the vertical direction, there is always a negative acceleration of minus 9.8 meters per second squared. And that's it. Cool.